Hello everyone, welcome to the week second, which also have our second module, that is characteristic of sensor. This is the first lecture of this module. We will have 5 lectures on this particular topic in this course on microsensors and nanosensors. When I ask you what do you understand by characteristic of sensors, okay, so the end user can say that anything which define its usability, like its sensitivity, selectivity, reproducibility, repeatability, how long it can perform, okay, so the lifetime of the sensor, okay, shelf life of the sensor, those things are defined as characteristic of a sensor. So if you see, these characteristics are considered as static characteristic, okay, because it is not part of the transient response of the sensor, okay. Similarly, I can have dynamic characteristic of a sensor. This particular module will focus on static characteristic of a sensor, okay. So by considering some specifications, there are various characteristics of a sensor. Some of the characteristics are shown on the screen. Transfer function, okay, sensitivity, calibration, span, which is also known as full scale input, then FSO, full scale output, accuracy and precision, hysteresis, linearity. With linearity we have non-linearity also, okay. We will define linearity in terms of non-linearity, okay. Then saturation, repeatability. With repeatability we will also have reproducibility, we will define that also, okay. Deadband, resolution, okay. Output impedance of a sensor. Output impedance is very important characteristic of a sensor because this output impedance will define the complete setup of interface circuit, okay. So we will see what is output impedance, okay. Output format, it means that the output of the sensor is in which electrical form. Is it charge, is it current, or is it voltage, okay. Then excitation, reliability, uncertainty, and so on, okay. In this particular module, we will see this characteristic in little detail. This characteristic that I am discussing is independent of the sensor, will define for that particular sensor, which we will discuss from module 4, okay. First, let us understand what do you mean by transfer function, okay. So when I say transfer function, it is an input-output relationship of a sensor. We know that output of sensor is nothing but its response, okay, and input is stimulus, okay, or the stimuli that we apply, okay. So it is basically stimulus response curve of a sensor. It can be mostly in the graphical format, but it can be some represented in the form of table or some mathematical function, okay. So the relationship between a stimulus, I am calling it a small s, and output electrical signals, which I am calling as capital S, is established by a transfer function, which is say capital S is equal to some function of S. This function can be linear or non-linear. Based on that, I will say that the transfer function of the sensor is linear or non-linear, okay. Consider this one of the example. You have output versus input or stimuli, and this is denoted by a function Fs. I can clearly see that this Fs is non-linear in nature, okay. So I can say that S is equal to Fs, or S is a function of Fs, where Fs is a non-linear function, okay. Mostly we will discuss in this course linear transfer functions only, because this is mostly a UG level course, okay. So linear transfer function can be like S is equal to A plus Bs, where A is the intercept, means the output signal when input is 0, and B is the slope, okay. B is also known as sensitivity of the sensor, okay. So if I have to define the sensitivity, I can say that the linear part or the slope of the linear part of this output versus input curve can be called as sensitivity, okay. For nonlinear transfer function, you do not have a defined slope, okay, means B is not fixed, okay. So at any defined input, say the small s is defined at particular instant, say at this particular moment as s naught. So linear transfer function can be in this form, like capital S is equal to a plus b small s, okay, like this particular equation, okay, where a is the intercept, means the value where the output signal, value of the output signal when input is 0, and b is the slope. This b, which is the slope, is also called sensitivity of this sensor. So if I have to define the sensitivity, I can say that the slope of the linear part of the transfer function is nothing but a sensitivity, okay. For nonlinear transfer function, b is not fixed, right. So at particular instant, okay, I can say that s is equal to s naught at particular moment, okay, and at that particular moment, say in this curve, say if I have to calculate, you know, slope at this particular instant, I will just put the value as s is equal to s naught, and at that particular input I can define b as differential of capital S or the function fs, okay. So d by ds of capital S at s is equal to s naught, okay. By this I can calculate the sensitivity of a nonlinear transfer function sensors, okay. So nonlinearity cannot be ignored for the sensors, okay. So you cannot say that your sensor has always linear transfer function. It can be nonlinear also, okay. So a nonlinear transfer function can be approximated by multitude of linear mathematical functions, okay, and linear piecewise approximation is an effective method to solve nonlinearity issues, okay. It involves breaking of nonlinear function of any shape into sections and consider each section as linear, okay. So let us consider this, let us try to understand this with an example. Consider this output characteristic of a sensor, okay. I can clearly see that the function fs is nonlinear in nature, okay. Now I can do a linear piecewise approximation, okay, and I may break this function into different linear regions, okay. So for example, I can say that, okay, from point A to point B, this sensor has linear characteristic. Again from B to say C, it is again linear, but of course there may be a change in the slope, okay, or the sensor may have different sensitivity from point A to B, and then this will be different from the sensitivity from B to C. Similarly, for C to D, I may have a different sensitivity or the slope. Again, I may have a different slope from another section D to E. For every region, I can have a input characteristic, say input, this is S1 to S2, okay, and for that I can have a output characteristic. So this is capital S1 to capital S, right. Similarly, I can find for the region B and C, and C to D and D to E. Similarly, for any, you know, shape of the transfer function, I can do this linear piecewise approximation, okay. So now I have basic understanding of a transfer function, okay. Let us see another characteristic of a sensor, which is calibration. Let's understand the usability of calibration with one example. Say to measure temperature with accuracy of say plus minus 0.1 degree Celsius with a sensor having a rated accuracy of plus minus 1 degree Celsius, okay. So if I give you this sensor and I tell you to measure with this particular accuracy, can we do this, okay. The example is very simple. I have to measure some temperature with accuracy of plus minus 0.1 degree Celsius, okay. However, the sensor that is provided to you has accuracy of plus minus 1 degree Celsius, okay. The question is it possible, okay, because the measurement that I have given to you is require more precision, okay, or more accuracy, okay. However, the sensor itself has poorer accuracy. Okay, so is it possible to use it? The answer is yes. Okay, is it possible to use it? The answer is yes. I can use the sensor with having accuracy of plus minus 1 degree Celsius for measurement of plus minus 0.1 degree Celsius. Okay, and this sensor has to be calibrated in this way. Okay, or in one particular range, it may have sensitivity in this range or accuracy in this particular range. Okay, so calibration has that much importance. Okay, let us try to understand that how it is important. Okay, calibration of a sensor, a good calibration, okay, minimizes errors associated with the measurement. Okay, it determines the specific variables that describe overall transfer function of a sensor. Okay, so it helps us in finding actual transfer function for a device, for a sensor. It also adjusts a sensor to perform accurately and consistently over the time. So you might have heard that the sensor employed at some particular place is working not in good manner, but at the same time the person is saying that sensor has not gone bad yet, but it has to be calibrated again, or it needs recalibration. Okay, so calibration is very crucial for a sensor. Okay, particularly it helps in finding the variables for the transfer function. Okay, example is for a temperature sensor, say voltage is A plus BT, where T is the temperature. It is not essential to calibrate a sensor at many input points. Okay, so for this particular sensor, if I want to calibrate, I do not have to calibrate at all the point where in the range where it is operating. Okay, for a known reference source, it is sufficient to calibrate at just a few input stimuli. Okay, input output points lies on actual transfer function. Okay, there are various methods of calibration. Mostly there are three standard methods of calibration. The first is 1-point calibration, then we have 2-point calibration, and we have multi-point curve fitting. Okay, there are three ways for calibration, particularly for this microsensors and nanosensors. Let us understand this 1-point, 2-point and multi-point curve fitting calibrations. Okay, let's see 1-point calibration. Okay, it requires a single point for calibration, which can be applied for the rest once offset is adjusted. Just have a look at the one of the characteristic or the transfer function characteristic of a sensor. You have a sensor output versus measured parameter. You have the actual response. The blue line shows the actual response and the red line shows the ideal response. So you already know the ideal response, and by the measurement you have found the actual response. You are seeing that both are parallel. Okay, so for this kind of sensor, just 1 point is more than enough for calibration. I will just do offset of this point, and my actual response and ideal response will overlap. Okay, this is mostly used for linear sensor, which is limited up to certain range of measurement. Okay, some examples are temperature sensors. Okay, where control system keeps the same temperature for certain period of time. Okay, nowadays this is also possible through some certain feedback interface circuits. Okay, now let us see a 2-point calibration system. Okay, it is a complex than a single point. It rescales a sensor output for 2 points instead of 1 point. Okay, it helps to correct both offset and slope and can be used for linear output sensor. Just have a look on reference and the measured value. Okay, you have a reference value and the measured value. You know the low and high. Okay, you know the low and high. Therefore 2 point is more than enough to bring the actual response to the ideal response. Okay, that is why I have mentioned it as a 2-point calibration system. Okay, so temperature sensors calibration with the ice bath and boiled water. Okay, so one you know that around 0 degree Celsius and another you know around 100 degree Celsius. So you know low and high. Okay, so these 2 points are sufficient for calibration of this kind of system. Then you have more complex calibration systems where you need actually multi-point calibration. Okay, so it requires some curve fitting and use for sensor with non-linearity over the range of the measurement. Okay, thermocouple is one of the important example for which needs multi-point calibration. Okay, then let us see some types of calibration of sensors. Okay, one of the type of calibration is linearity calibration. Okay, it is used to measure the linearity over the full range of its measurement. Okay, so depending on which characteristic you require, okay, you can have different type of calibration. So linearity calibration helps you to measure the linearity over the full range of its measurement. Okay, similarly we have a span calibration. Okay, span calibration is used to determine the full range of measurement. Okay, so say if I have a temperature sensor, say it can work from minus 200 degrees Celsius to 800 degrees Celsius or so. Okay, what I have to find is the span, which is 800 minus 200 degrees Celsius, means it's around 1000 degrees Celsius. Okay, then we have zero calibration. Zero calibration is basically used to measure the offset. Okay, then I have a sensitivity calibration. Okay, it is used to determine the sensitivity. I have defined the sensitivity some time back. Okay, sensitivity is defined as the slope of the linear region of the transfer function. Okay, so if your transfer function is linear, the slope itself gives the non-linearity. If the transfer function is non-linear, then you have to find particular range in which you find you want to find the sensitivity. Take the slope in that particular range, or find the differential value for the function. Okay, and find it at that particular input. Okay, say for temperature, find it at t equal to 100 or t equal to 80 and so on. Okay, so sensitivity calibration is used to determine the sensitivity of the sensor. Okay, similarly I can have temperature calibration. Temperature calibration is used to determine effect of temperature on the performance of a sensor. Okay, and please note that for all of this calibration I need one reference. Okay, then there is another kind of calibration, which is hysteresis calibration. Okay, it is used to measure hysteresis. We'll discuss what is hysteresis. For the time being, please consider it as difference in output at a given input if input is approached from different directions. Okay, we'll see what hysteresis means and what is hysteresis error in the coming slides. Okay, and then we can also have non-linearity calibration, which is used to measure non-linearity in the sensor over the range of the measurement. Okay, then I also have a repeatability calibration, which is used to measure repeatability, which is the degree at which a sensor produces same output for the same input over the long time. Okay, we'll see the repeatability in some time. Okay, please note that all this require standard reference. Okay, so reference standards are always required for calibration of sensor. It is another calibrated tool which is used to make reference readings for comparison. Okay, for example, calibration of a thermistor. Okay, let us see thermistor calibration using reference standard. Okay, for this kind of calibration, please note that we have to do some invasive treatment of the sensor. Okay, so in this process, a thermistor is immersed with fluid, which is of course non-conductive. So a thermistor is immersed in a fluid bath with controlled temperature. Temperature of the bath is monitored by precision reference thermometer, as you can see. Okay, resistance of the thermometer is measured by a ohm meter, which is part of the calibration instrument. Okay, a grinder is used to remove some of the material from the thermistor, and due to this removal, there is a change in its electrical resistance at specific bath temperature. Okay, the grinding stops and the calibration is finished when the thermistor resistance matches a predetermined value. Okay, now the thermistor response matches the ideal transfer function. Okay, so by this invasive method of calibration, I can calibrate my thermistor. Okay, similarly, there can be other reference standard for other sensors. Okay, I hope that calibration is clear to you. With calibration, there are some errors associated. We call it calibration error. Okay, it is the inaccuracy permitted by a manufacturer when a sensor is calibrated in the factory. Okay, this is a systematic error. It means that it is added for all possible real transfer function for the sensor. Okay, it shifts the accuracy of the transfer function for each stimulus point by a constant. Okay, this is not necessarily a uniform error over the range. It can be non-uniform also. Say for example, in lower stimulus range, it can have different values and at higher stimulus values it can have different values. Okay, it depends on sensor to sensor. It may change depending on type of error in the calibration as well. Okay, I hope that this calibration error is also clear to you. Let's move towards another important characteristic which we have been using since some time, which is span. Okay, span is also known as FSI, full scale input. Okay, so a dynamic range of stimuli that may be covered by a sensor is called a span or an input full scale. Okay, we usually denote it with Fs. Okay, it represents the highest possible input value which can be applied to the sensor without causing unacceptability of large inaccuracy. Okay, again let us understand this with the example of a gas sensor. Okay, like consider a ammonia monitor. Okay, I have again a two terminal device which can act as a very good ammonia sensor. Okay, the transfer function of the sensor of this ammonia sensor has been taken for output for the input from say certain value of say 4 ppm of ammonia to say 40 ppm of ammonia. All right. So usually in the specification sheet of the sensor, the span will be represented as 4 ppm to 40 ppm. Okay. So does it mean that the sensor do not work when the ammonia concentration is just less than 4, say it is 3.5 or a little bit higher than 40 ppm or say 41 ppm? Okay, it still works. Okay, it will still work. Okay, however, the manufacturer has defined the span from 4 ppm to 40 ppm considering various information in mind, including the accuracy of the instrument. Okay, so usually the system or the sensor has to be operated in this particular range, but it doesn't mean that it will not work above this range. Beyond this range it can still work, but then you are compromising with the accuracy of the sensor. Okay, so usually for larger range of the dynamic range, usually the data is represented in the dB, decibel. Okay, by definitions, decibels are equal to 10 times the log of ratio of powers. 1 dB is equal to 10 log P2 by P1. Okay, in similar manner, decibels are equal to 20 times the log of force or current or voltage. 1 dB, depending on the signal, we have 20 log S2 by S1. Okay, so I think span is clear to you. We have another characteristic of the sensor, which is full scale output, FSO. Okay, full scale output is the algebraic difference between the electrical output signals measured with the maximum input stimulus and the lowest input stimulus applied. Okay, so this must include all deviation from the ideal transfer function. Okay, then we have accuracy and precision associated with my sensor. Okay, so accuracy is very essential characteristic of a sensor. Okay, usually accuracy is defined in terms of inaccuracy, and inaccuracy is measured as the highest deviation of a value represented by the sensor from the ideal or true value of a stimulus at its input. Okay, so usually accuracy and is always associated with another word which is precision, and it is confused to be same, but they are not same. Okay, let's see a basic difference between accuracy and precision. Okay, so accuracy has to do with how right your answer is. Okay, precision has to do with how consistent your answer is. Okay, similarly for a sensor you can say that accuracy has to do with how correct the measurement is, and precision has to do with how consistent the measurement is. Now you have to decide what you want. Okay, usually in ideal case you want a better accuracy. Of course it should also come with better precision, but you can compromise little bit on precision, but you cannot compromise at accuracy. Let us understand this example of accuracy and precision with some figure. Okay, let's see, let's analyze this figure in brief. Okay, consider this figure A. I am calling it A, B, C and D. Okay, let's consider figure A. Okay, just see that this yellow part is the aim. Okay, I want to hit this particular area. Okay, so there are 4 people, and they are given 4 different trials to hit this area. Okay, the person A hits this area, okay, with accuracy as well as precision. So if you see, all his 4 trials are accurate and precise, because every time he is able to hit the yellow area. Okay, person B, if you see, his values or his hits are accurate but not precise. If you see, there is some deviation. Okay, there is some distribution in the hit. Okay, so it is accurate because every time he is hitting the yellow area. Okay, but it is not precise. Okay, this is also acceptable. Okay, let's see person C. Okay, this person is hitting continuously the blue area, means he is very precise. Okay, but if you see, he is not accurate. He would have been accurate if all these 4 hits were in this area. All right, so person C is very precise but not accurate. Okay, now see person's D case. This person is hitting once at this red area, thrice at the blue area. Okay, means he is neither accurate nor precise. Okay, now replace this concept of person with sensors. Now you take this example with sensors. So you have sensor A, B, C and D, and the measurements are if the measurements are say in certain range of value, I can say it is accurate and precise. If it is beyond that value, okay, I can say that it is not accurate. Okay, but if the same value is coming every time, I can say that it is precise but it's not accurate. Okay, so with this I hope that a concept of accuracy and precision is clear to you. Okay, with this we'll stop this lecture and we will meet in the next lecture with some more static characteristic. Okay, thank you.